Alrighty. So let's look at the first problem. So a ladder of length 10 feet is leaning against a wall. Suppose the bottom of the ladder slides away from the wall at 2 feet per second. How fast is the top of the ladder sliding? How fast is the top of the ladder sliding down the wall when the top, this is such long problems, top is 8 feet from the ground? Okay, so this is our typical ladder problem. This is very standard. All right. So if we want to draw a little diagram, we could do that. Here's our wall. And here's our ladder. Okay, so the first thing we're going to do is we have to somehow, so first of all, I didn't say this in the problem, but we're going to assume that the ladder never loses contact with the wall or the ground. If some of you have taken physics, you realize that that's actually not true. That's not possible unless the ladder is actually bolted or something. So anyways, so first we have to somehow convert all of this information in the problem to mathematical sentences, right? Or else we won't be able to solve the problem. So the first thing I have to do is if I want to be able to even translate any of these sentences into mathematical sentences, right? In other words, equations, I have to somehow introduce certain variables, right? So what types of variables would you introduce in this problem so that you can translate all of these English sentences into mathematical sentences? So I'll give you one. The length of the ladder. That's pretty easy. So the length of the ladder is 10. Duh. So we're going to label that with 10. Simran says X and Y could represent the length and the height. Okay. Right. Why would I introduce those variables? Well, the second sentence is talking about the bottom of the ladder sliding away from the wall. And then I'm asked about something about the top of the ladder sliding down from the wall. So it seems that these two lengths, this horizontal length and this vertical length, are probably important. So we'll call them X and Y. Okay, so now let's talk about what about, I want to find what are the relationships between these variables, what is the information in the problem, right? I want to kind of go through each sentence of the problem and translate all of the information in the problem into mathematical sentences, right? Okay, so let's do that. So given information, so what are we actually told? So let's go, so Camille has a question, but we'll get to that in just a second. So let's go sentence by sentence. The first sentence says a ladder of 10 feet, a ladder of length 10 feet is leaning against the wall. Is that piece of information already built into the problem? Yes, it's already in my diagram. I don't need that piece of information anymore, so let's skip it. Next sentence. Or actually, what we're gonna do is we're gonna look at clauses. You all take writing classes, right? You know what a clause is, right? That's not exactly a sentence, but you know what a clause is. Adam, do you know what a clause is? Yeah, he's that guy that gives you presents on Christmas. Right? No, the clause. Okay, suppose the bottom of the ladder slides away from the wall 2 feet per second. So given the variables we've introduced, x, y, and 10, 10 is not really a variable, it's a constant, but how would you translate this sentence? Suppose the wall, remember, we are trying to translate this into mathematical language. In other words, I want an English sentence becomes what? A mathematical equation, right? That's the analogy or the analog of a sentence. So can we write down a sentence that describes this? And Simran says dx dt equals 2 feet per second, right? That is correct. How did I know this had to do with, first of all, let's ask a few things. How did I know this had to do with the variable x and not y? What tipped you off in this sentence that this is about x? It's important you understand that. Okay, I would say, Simran, let's see. So a few people saying bottom of the ladder. So I would say, yeah, the phrase bottom of the ladder is kind of the tip that it's x, right? Bottom of the ladder sliding away means that this point is moving that way. And so that has to do with this length, right? That length x is going to be changing over time. And like Justin actually said, the distance from the wall is changing. So how did I also know that it was not just having to do with x? What about dx dt? Why am I writing ddt here? Why am I having dx dt? What in that sentence gave away that I need a dx dt and not just something with x or maybe something else? Right, so like Jacqueline is reminding us, we're talking about a change with respect to time. Ayana is saying it's the rate at which the ladder slides away, right? I also actually give you a rate of change here, right? Feet per second, right? Distance over time, or I'm telling you a velocity. So in other words, I'm telling you how a certain position or length is changing over time. Okay, so that's it for that sentence, right? We've gotten everything we want. What if, now I want to actually ask another question. Let's suppose for a moment, just temporarily, let's suppose that the correct answer was -2. What would have the English sentence have said for you to have interpreted it correctly as -2? So the English sentence would have had to say something different for you to conclude -2. Okay, Anna says towards the walls. Caleb says slides closer. Exactly. Because that negative would imply that x, that variable is actually decreasing, right? A negative of derivative implies decreasing. So that means if x is decreasing, that means the bottom of the ladder would have been sliding towards the wall, right? So that would have been a different description. But because it's sliding away from the wall, we actually get this just +2. Okay, so that sentence is done, right? So we can kind of cross it out from our minds. All right, the next clause. So now we have the question. How fast is the top of the ladder sliding down the wall? That is the first clause, right? The when the top of is 8 feet from the ground is actually a separate clause, right? What is this highlighted clause actually telling us or asking? It's actually a question, right? Because the whole thing is a question. What is this asking us to find? dy dt, that is correct, right? It's asking how fast is the top of the ladder sliding down the wall. So it's actually asking us dy dt, right? So I'm going to write here dy dt, oops, equals question mark, because that's what we want to actually find out, right? And this isn't proper notation. In mathematical notation, we'll have this question mark, but I'm going to use it as an abbreviation as saying our goal is to find dy dt, right? That is our goal. Now, it's not just I want dy dt. Keep in mind that x and y are functions of time, and I don't want dy dt in general. I want dy dt at a very specific time. What specific time do I want to know dy dt at? 8 feet? That's not 8? So give me dy dt when 8. Does that make sense? Give me dy dt when 8. when y equals 8. That's correct. Right? It says when the wall, sorry, it says when the top of the ladder is 8 feet from the ground. So at the instant that y happens to be 8, I don't know what time that is, right? I can't, right? Usually we think of these problems as, in our daily lives as, tell me what's happening 3 seconds later, or tell me what's happening in a minute. No, we're actually not going to say that. We're saying, all right, tell me what's happening when the top happens to be 8 feet from the ground, whatever time that is, right? So this is describing a certain time when y equals 8. I don't care what time that is, just whatever time that happens to be. It could be 2 seconds from now, it could be 3 seconds from now, whatever. Okay, so that's the given information. And then there's a little bit more that's given to us, and that's kind of hidden almost. And that's a relationship between the variables. Now, the problem is not going to tell you, oh, these are your variables and this is the equation that relates them. No, they're going to give some description. And that was kind of hidden in the fact that we have this straight ladder of a constant length. We have a ladder kind of resting on a wall, right? Just the whole description of the problem as a whole kind of describes to you there's a relationship between X and Y. And usually this is evident from the diagram, once you draw a diagram. So what relationship do I have between X and Y in this problem? And this has to be true for all time. Pythagorean theorem, right? So for all t, what has to be true? Give me an equation that is true for all time. Right, x squared plus y squared equals 100. So that is going to be the equation that we use to essentially solve this problem. Okay, now I'm very careful to say this holds for all time, right? Why is it important to hold for all time? So let me give you an analogy. So the most common mistake in these types of problems is substituting in information, substituting in some of this information too early in the problem. For instance, a student writing down maybe x squared plus 64 equals 100, and then thinking they can start taking derivatives. Or treating the ladder as if it were not a constant, or the length of the ladder as if it were not a constant, right? Right. Why does it not make sense to do that? So, for instance, I eventually want to find out what is happening at dx dt, or I want to find out what's happening with dy dt, given some information about dx dt. If I were to give you, say, an equation that said x squared plus 64 equals 100, right? That's for y equals 8. That is true only at one specific time. So it's as if I took like a photograph of this ladder at one specific time, and I gave you this one photograph, and I asked you, okay, from this photograph, figure out how fast the top of the ladder is moving. I mean, you can't even tell from the photograph whether the ladder even is moving, right? So the analogy that I like to tell students is the idea of using this equation, x squared plus y squared equals 100, using an equation that holds for all time, it's actually as if I used my phone and I took a little movie, right? I recorded the ladder sliding down and I gave you the entire movie and I said, okay, use this 2-minute video and scroll to the part where y equals 8, and from the video try to figure out how fast y is changing. Now you actually can do it, right? Because you have a whole description of the ladder for all time, right? You can kind of like look what's happening before and after in that video. So that's why you always need an equation. You always must start with an equation that holds for all time. And you should forget about all this information for the time being, right? Because that is information that holds only at that photograph, that snapshot of time. And that is not what I want to deal with right now. I want to deal with the whole movie first. Okay, so what do you think we might do here? So we have to somehow introduce dx dt and dy dt. Implicit differentiation. This is right. That's why we did implicit first on Friday. And we're going to do it with what? With respect to time. So please make sure you understand this now. X and Y, we're not considering Y as a function of X. We're considering X and Y as functions of time. Everything is a function of time. So this equation actually says X of t squared plus Y of t squared equals 100. I don't know what these functions are. I don't really care. I don't need them. But they are functions of time. I am not thinking of Y as a function of X. So when you differentiate X squared, you do not get 2X, right? When I differentiate X squared, what do I get? I get 2X times dx dt. That's correct, right? Because what is the derivative of X of t squared with respect to time, right? It's 2X of t times X prime of t. Please don't use the prime notation, though. Please use the ddt notation. Prime is usually saved for if I'm thinking about Y as a function of X only, and I only have those two variables. They may have mentioned in your physics class, when you're doing time derivatives, sometimes you actually put a dot above. So you might write this as 2x x dot. So a dot above a variable actually can also denote a time derivative. Has anyone seen that in their physics class, a dot to denote a time derivative? And if you want two time derivatives, you just do two dots. So Newton's second law is, mx dot, is the net force. So that's how you would write that. Okay. So anyways, so let's continue to differentiate this. What is the derivative of y of t squared? It's not 2y. The derivative of y of t squared is not 2y. It's 2y times dy dt, right? Can we remind everyone why is the dy dt and the dx dt, why are they appearing? What rule of differentiation is causing them to appear? Chain rule, that's correct, right? Like in this case, the inside function is x of t and the outside function is the square. So the dx dt is coming from chain rule, the derivative of the inside function. Same thing for y of t. Then obviously on the right-hand side, I get 0. Derivative of 100 is 0. So now I have two possible equations here, right? I have x squared plus y squared equals 100, and I have equation 2, 2x dx dt plus 2y dy dt equals 0. And the important thing is that these equations hold for all time. And again, in this analogy that I was talking about before, x squared plus y squared equals 100. That's as if I gave you the whole movie on my phone, and then you have now extracted from that movie some information about the velocity of the ladder, right? I gave you a movie that gave you the positions of the ladder, and now you have extracted the velocity of this ladder, right? The x and y velocity of this ladder. Okay, so now that we've actually gotten everything that we need for the whole entire movie, now we can focus attention on what we want, right? I want dy dt at a specific time. So now we can substitute our specific information because now that we have everything from our movie, now we can focus on that one time, that one instant, that one snapshot in time. So now we substitute information specific to described time. All right, so let's remind ourselves what's happening here. So we have equation 1 and equation 2, and they're going to become equation 1 star and equation 2 star. They were x squared plus y squared equals 100 and 2x dx dt plus 2y dy dt equals 0. So what are we doing here? In these two equations, right, what are we doing? We're substituting our given information, which was dx dt equals 2 and y equals 8. So what happens? Now we get two different equations. So again, the equations on the left hold for all time. The equations on the right hold only for the specific time. So let me actually even remind you of that. Right, one time only. So what equations do we get? We get x squared plus 64 equals 100. And we get, so dx dt, remember, is 2. So we get 4x plus 16 dy dt equals 0. And now what is our goal? So now that I have these two equations that hold only for that one time only, what was our goal, recall? It was to solve for dy dt. So again, notice that if you had plugged in the information too soon, you would have actually gotten this equation, 1 star, and then when you differentiate that, you get nonsense, right? You get 2x dx dt equals 0. That makes no sense because this equation actually doesn't even tell you, that equation actually tell you x is just what? X is just 6. It doesn't even tell you x is changing, right? So that's why everything has to be done for the general situation first, then you differentiate, and then you plug in. Okay, so solving for dy dt is just a matter of algebra. I mean, this is very easy. If I want to solve for dy dt, I obviously need x in this equation, but I can get x from the first equation, right? So let's just write that down. So from 1 star, we get that x has to equal 6. Then from 2 star, so if x is equal to 6, what do we have? We have 24 plus 16 dy dt equals 0. So dy dt is what? Negative 3/2. And that's, what are the units? Let's make sure we understand that, feet per second. Hirsch, what does this negative signify to us?
It signifies like a negative slope, or
A
like,
negative slope, but yeah, but in the context of this problem,
yeah, like it pretty much moves towards the wall,
what moves towards the wall?
the ladder.
Well, which part of the ladder? The top of the ladder is moving towards the wall?
No, all of it.
All of it? The whole ladder is moving towards the wall?
I mean, I guess. I mean, I don't know, but
Okay, so who wants to help him out? Right, we're talking about why. Jessica, what do you think? What does that negative in dy dt signify in the context of this problem?
It's because it's because the ladder's sliding down.
Okay, good, right? It's because the ladder is sliding down, right? This tells you that y, the negative tells you what? Decreasing. The variable y is decreasing over time. So that length y is shrinking over time. In other words, physically what's happening is the top of the ladder is actually moving down the wall, which makes physical sense, right? If you had gotten a positive answer for y, that would have made no sense. Now, as a kind of very technicality that doesn't really matter here, the actual problem asked you how fast is the top of the ladder sliding down. So the sliding down was actually already built into the question. So I'm actually going to say as my final answer, although this really doesn't matter. The top of the ladder is sliding down at 3/2 per second, 3/2 feet per second. Top of the ladder. right? I mean, you don't say the top of the ladder is sliding down a negative 1.5 feet per second. You can say that y is changing at a rate of negative 1.5 feet per second. You can say, but you can't say the top of the ladder is sliding down at negative 1.5 feet per second. That doesn't make sense, right? So it's just a kind of an English thing. Okay, so that's it for that problem.